Next, we have Ming Chen from Stony Brook University, who's going to talk to us about secure middleware for wide area network attached storage.
Hey.
23 minutes.
Okay. Good morning. Thanks for the introduction. So I'm very glad here today to present our paper SYSTOR16, a secure middleware for wide area network attached storage. It's a work in collaboration with Professor Day1 from Stony Brook University and Aaron from Nutanix and Colin from EMC. So this is the outline. We'll talk about background and motivation and design implementation and evaluate its performance and draw conclusion from that. So nowadays clouds are really popular. It has a lot of advantages as I listed here, including from accessibility all the way to scalability. However, it's not perfect, and one of the biggest concerns is security. And many security concerns are inherent to the nature of cloud. First is cloud is opaque in the sense that customers does not have access to the physical machines and devices. And the second, cloud are shared among multiple tenants. So your VMs might be running in the same physical machines with other VMs that might be malicious. The third, cloud expose large exploit surface to attacks because cloud's infrastructure are accessible over public network by all sorts of people. The third is that clouds are not only opaque, but also very complex, and thus may contain tricky bugs difficult for customer to diagnose. And the security concerns are also intensified by high-profile incidents like data corruptions and leakage of user data. So SYSTOR16 is our effort to secure cloud storage. It focuses on the scenario when organizations with geographically distributed offices use untrusted cloud to store and share data. This model of saving data on untrusted server is not new and has actually been studied over the past decades heavily. However, there are new challenges in this cloud era. So the first new challenge is that the key sensitive of cloud storage is its low total cost of ownership. However, adding any security mechanism have performance overhead and might introduce costs that are not justify the usage of cloud. There are previous papers about that. So a cloud security scheme should be efficient and not introduce too much overhead. The second new challenge is the heterogeneous nature of cloud in both the client end and the vendor side. Thus, it's important for a security scheme to use open and standard technologies. The third challenge is that we have to be careful for not only attackers, but also the cloud's complexity. So when modern storage stacks are already deep and complex, the cloud can be much more complex. In cloud, all these storage stacks can be replicated. Replicated vertically because of virtualization. So nowadays, it's not uncommon for cloud vendor to use container to manage their VMs, and inside the VM, the customer of that VM use again containers to provision that applications, and also these are replicated horizontally as well because of the network distributed system inside cloud. So now we go to the design of SYSTOR16. So this figure is showing the architecture of SYSTOR16. We choose to use a middleware architecture for SYSTOR16, and in this scenario, in each office we have a SYSTOR proxy sitting between clients and the cloud, and it actually is inside the same on-premise network with the clients, and each office has one proxy instance, and that has a lot of advantages as we are shown here. Using a middleware will simplify our management as securing a fewer number of proxies is much easier than secure a large number of clients. It also simplify key distribution because we only need to manage keys on those proxies, and it also fit well with one caching and the firewall architecture. So one uncommon design choice we made in this is we use NFS, especially V4, not only between clients and the proxy, but also between the proxy and the clouds, which may be uncommon at this stage. And we have multiple reasons regarding why we do that. First, we think V4 has advantages over vendor-specific key value stores. So NFS V4 first is open and pervasive and standard, and is POSIX compliant and has good cross-platform interoperability, and also suffer less from data or vendor lock-in than using vendor-specific API. It's also optimized for WAN, so when we use it across WAN in cloud, it's convenient. It has advanced features for that. It also have richer semantics, and we believe that cloud storage is still in its early stage, and the current popularity of key value store is mostly due to its simplicity. As the technology advances, I think applications would like to use more rich semantics for storage, because that will simplify their application development so that they can develop the same app with fewer lines of code in less time. Actually, there's already an example. There's Amazon NFS V4 service called Elastic File System. I think it's in beta right now. A richer semantics also means more optimization opportunities. Like a good example is server-side copying. So usually we do copying in network distributed thing. We have to move data around, but with a higher semantics saying, hey, we're doing copying, then we don't have to go through the network round trips. Yeah. NFS V4 also have advantages over older versions, like easy administration and more scalable and more secure. So this is showing the data path of Seminas. We implemented it as a stackable file system layers. So these are Seminas. So when clients issue NFS write requests, it goes to the file system layer. The first layer is a caching layer, which is optional, but we add it. But we add it because it's each work hand in hand with security in most scenarios. And now we added an authenticated encryption layer, which will do encryption and authentication at the same time. And then after that, they will write the ciphertext as well as the message code, authentication code together to cloud. And the read path happens reversely. So Seminas manage actual security metadata. First, each Seminas proxy has a unique ID and a key pair, and each proxy knows the public key IDs and the public keys of all other proxies. Because there are only a small number of proxies, those keys and IDs can be easily distributed via a secret channel or even just manually. And each file, we use a unique symmetric file key for doing real encryption. And rows per file key are encrypted and protected by the master key pairs of each proxy. And we break files into blocks and apply GCM into each block. GCM is a standard authenticated encryption mode. So as seen here, it will just generate the MAC and doing the encryption altogether. And so because we break the file into blocks, so this is we have to organize the metadata of each file and each block as shown here. And the most important part of the file header is pairs of Seminars ID and encrypted file key. So all the encrypted file keys here just encrypting the plaintext file key of that file. And whenever a proxy need to get the key, you will just look into this and find its corresponding entry, and then retrieve the real key by decrypting this EFK. It's a kind of a standard way to sharding key security. There are some other metadata information in the header as well. And for each block, we generate the ciphertext as well as some per block metadata. So we performed two NFS-v4-based optimization. The first is called data integrity extension. It's related to the idea of data integrity feeds, which are 2 8 bytes associated with each 512 byte sectors. These 8 bytes has existed for a long time, but previously it was used mostly by storage vendors and inside for generating checksums over the sector. However, nowadays the storage stack are becoming so complex that there is a trend of extending those bytes to upper layers, so that not only the storage vendors can use it, but also the storage upper layers like file system or even application layers can use these bytes to protect the data integrity. So this, on the right side, I'm showing a figure of how we use it. So basically, when the clients write a block of data, we will encrypt it and generate an authentication code for that block of data and attach it to the end. And this message authentication code and the block and the ciphertext data will be sent over the network to the server, and the server will write it, pass it through the operating system and write it all the way back to the storage device. So in this way, we achieve like end-to-end integrity protection of the whole NFS path. And this way of saving per block method has some advantages over other alternatives, which I'm not going into at this time. So another optimization we made is to using compound procedures, which is a new feature in NFS-v4. It's very, the basic idea is to put multiple file system operations inside one RPC, so that roles doesn't have to suffer extra round trips over network, and it's very friendly to wide area network. So we use this compound procedure in seminars to writing the per file metadata, which is the file handle, so that file header. So whenever we need to operate on the file header, we will merge that operation of the file header to the previous operation and send it over the network inside one compound, so that it does not cause extra network round trips when we are manipulating this metadata. Yeah, so now we go to the implementation. So we implemented seminars on top of NFS Ganesha, which is a userland NFS server. It has a backend architecture called file system abstraction layer, which is similar to VFS in Linux kernel, and it has some backends inside it, and one is FSL VFS, which is basically using system calls to file system calls as the backend, and the proxy backend, which is use another file NFS service as a backend, and of course we are using this proxy in our case, and so we implemented stackable file systems on top of a proxy, a caching layer and a stack NFS layer. And then we also changed this proxy layer to support DIX. And we also changed the NFS server end to support DIX, and changed the kernel to accept those extra integrity bytes. And in particular, when it comes to implementation of DIX in NFS, we are using the read plus and the write plus operations. These are two operations proposed by NFS 4.2. It's not a standard yet, but it's kind of emerging. So these are the implementation details. We added caching and securities in Ganesha, and we also added multiple stackable layers support inside Ganesha, and we extended DIX to NFS and use CryptoPP for implementation. And we ensure our implementation passed all XF test case applicable to NFS. The XF test case is a general name. It's just that it originally comes from XFS. It's actually applicable to a lot of file system implementation. So, and it's take about 25 months of 3 graduate students over 3 years, and we added 13 lines of C and C+ code into Ganesha and fix several bugs inside Ganesha and in the kernel. So now we go to the evaluation. So this is our experimental setup. In our setup, we have 5 clients, 2 of them with 1 gig RAM and a 10 gig NIC, and the proxy has a 64 gig RAM and use SSD as a cache, and the server has 60 gig RAM. And on the server side, when it comes to the DIX storage device, which needs to be a physical device that supports the DIX protocol, which is not available in market yet. So what we did is we created a virtual SCSI DIX disk backed by RAM, and we evaluated them on the following workloads. And I'm going only to cover 4 of them, and the rest can be found in the paper. So the first workload is random read and write with different read-write ratios. I'm showing here for 2 figures. The upper one is with cache off, and the bottom one is cache on. And on the x-axis is the read-write ratio from write intensive to read intensive, and the y-axis is normalized speed. We are comparing similar to the vanilla, which is the FSL proxy, and to see how much performance overhead we introduce. So without cache, we are seeing a performance dropped between 46% and an occasion performance increase of 4%. I'm going into why it actually sometimes increase the performance. It's kind of an artifact we will talk about later. And one with cache, its performance is between -8% and +4%. The trend we can see here is that because we are very careful in not introduce any extra network round trips in our design, so that is very friendly with the wide area network. So when we increase the latency between the proxy and the cloud server, it actually the normalized speed actually increase. Well, actually, it's another way to put it is its overhead is smaller with larger network delay. So I previously showed that it's a little surprising that we actually increase performance sometimes, and we dig into the implementation, and it turned out that it's because of TCP Lego algorithm, which is an algorithm of introducing extra delay into network in the hoping of coalescing more data to send over over the network. And on this figure, I'm showing the number of threads on x-axis, which is relevant, and the throughput only y. And I'm showing 4 configurations, like baseline with and without cache, and seamless with and with cache. So with a smaller number of threads, they are the same, but when it comes to 100, we actually see seamless increased performance. That's because of legal algorithm, and that's also because of some particular implementation inside Ganesha, which is you use multiple threads that's sharing one TCP connection. And when we actually use the TCP flag non-delay, which basically disable legal algorithm, we are saying that they become the same. So this is an artifact which is kind of surprising to us as well. Yeah. This is the evaluation result of FileBench NFS server workload, which emulates the storage the storage workload experienced by an NFS server. And we can see here that without cache, we see a performance penalty between 8 and 17%, and with cache, we see a performance penalty between 18 and 26%. And because we are careful at not increasing network round trips, these overhead a decrease as the network delay increase, as shown here on the x-axis. So this is the web proxy workload in FileBench, and I'm showing 2 figs here corresponding to 10 millisecond and 30 millisecond network delays. And on the x-axis, I'm showing a gamma parameter shape. Basically, it's a FileBench parameter telling locality of the access patterns. The higher the value, the less locality in the workload. So that's why caching performance better when we go along the x-axis. So overall, we see that without cache, its performance is 4 to 6% lower, and with cache, it can actually be 9 to 19% better. Yeah, and that's so we propose the sameness to secure cloud storage, and we designed it to be a middleware and taking advantage of NFSV for compounds and data integrity extensions. We implemented it by adding security stackable layers and also extend DIX into NFS. And we evaluated it and showing a small performance penalty less than 26% in macro workloads, and an occasional performance boost by up to 90% due to the NAGO algorithm artifact. So there's a couple of limitations. First, our implementation right now is not safe against replay attack yet. The traditional way of fight against replay attack is doing a Merkle tree, and then you authenticate from the root. But that's very expensive in a wide area network. So what we are doing right now is to come up with an idea of synchronized file versions among the proxies, so that we don't have to be expensive. And we are also working on some other things, including metadata encryption and transactional compounds. And with that, I'm glad to take your questions. Yes.
You're doing the caching above your encryption, which means you're caching your data in clear text. I'm wondering why you didn't decide to do the encryption first and then cache the encrypted data.
Oh yeah. So in our so the question is why we are doing caching before we do the encryption. So I think it's yeah. So the reason is because we are treating the proxy as trusted. So the data saved here, which is on-premise network, is considered as trusted. So we think it does not break our thread model. That's the reason. Yeah.
Any other questions? Actually, I had a quick question. There's been some work on specifying the semantics of your file system, and I noticed you had, these XFS tests. Did you find difficulty making sure that you sort of weren't breaking the current NFS implementations?
Yes, we find some very tricky things in the caching semantics of NFS, and I think it's traditionally NFS using the file's change time to indicate that they should discard the cache or not. But when we are adding a header, we will change the change time. So we are kind of just very carefully maintain the change time to say we are not going to accidentally invalidate our cache. So things like that. But yeah.
All right, let's thank our speaker.
Thank you.